Our next speaker is Alon Herman from Tel Aviv University. He's going to talk about the ratchet-based ion pump.
So first, why is this important? Well, because separating ions is quite challenging, and there are quite a few applications where this is needed. Desalination is, of course, Desalination is, of course, in great need in both rich and poor countries. Current technologies are growing rapidly, but still face considerable challenges, especially the electrically driven technologies. More generally, highly selective separations can open the door to applications like extracting valuable metals, such as lithium and others, which are abundant in the ocean. Or purification of ground and wastewater from toxic elements, or even as part of desalination systems that reduce the need for post-remineralization. And many more applications could be imagined, including in biological or agricultural environments. So we believe that a new technology that will allow for selective and efficient ion separation could have tremendous value in many fields of interest. So our proposed device is based on an electronic ratchet mechanism. In order to have a net flux ratchet effect, you need two conditions. You need some spatially asymmetric force or potential acting on the particles. In our case, we'll use an electric field. And you need some sort of time modulation to drive the particles out of equilibrium, like an alternating power source. This is illustrated here with a simple sawtooth potential. So at the beginning, you see you have particles at an energy minimum. Then when you flip the sign, so they drift to both sides. But then if you flip again the sign with the right time step, then you see that some of the particles are going back to the same position, but some have moved forward. Okay, and this gives us, over time, a net flux to a certain direction. So, and note that these ratchets can work also with zero mean drift force. There are a few types of ratchets and more advanced asymmetries. Some were shown to have very high efficiencies, close to 100%. For example, with enzymes pumping ions in and out of cells. So ratchets are not new, but they might possess important advantages for highly selective ion separations, as we will show in this talk. And have never been demonstrated with ions so far. The basic design of the proposed device that we call a ratchet-based ion pump is presented here. It is the simplest membrane-based structure that can create the wanted asymmetric potential distribution. The design is based on a nano-porous anodized aluminum oxide wafer with metal contacts deposited on both sides. What we see here is the volume around a single nanochannel that allows for ion transport between two chambers with electrolytes. And the nanochannel here has two important effects. One is that there is a difference in the device screening length between the inside and the outside of the channel. And this is what creates this asymmetric potential distribution. So what we see here is the potential distribution near the right contact. And this is a well-known phenomenon in nanofluidics. And we also demonstrated it using a 2D axisymmetric console simulation where we solved the Nernst-Planck-Poisson equations in steady state. And this is for a typical case of 14 nanometer pore diameter and 1 millimolar KCl solution. And we consider the potential varies as a function of the pore radius. And this is where we also see the second importance of the nanoscale of the channel, that the electric field can penetrate and affect ions all the way to the center of the pore. Okay, you can see the blue curve in the bottom is the center of the pore, so it's not screened, and the pore is also being used for ion, or the middle of the pore is also being used for ion transfer. Now, let's see a simplified illustration of what happens. This is the mean channel potential now, near the same contact, and what happens when we start to modulate the source. So, starting from a negative potential, you see the cations are attracted to the contact. Now, when we flip the sign of the input signal, they start to drift to both sides, and then if you catch it in the right time, you get the ratchet effect. Okay, so this is the simplest structure that can give us this distribution and this ratchet effect. Obviously, we will want in the future to have more complex stacked device that can allow us with continuous sawtooth-like potential like we saw before. So we can see that this is a membrane-based design that is scalable and easy to fabricate. Just a second, okay. And we see that it's theoretically capable of generating a net ion current in steady state. And an important point is that this is without any energetically expensive Faradaic reactions at the electrons, since we can do this at quite low voltages. Okay. Okay. The wafers they can be produced with a variety of pore diameters and wafer sizes and thicknesses. The thin layer contacts are deposited using E-beam or sputtering. The right image shows a finished wafer with metal contacts, and next to it is the same image after sputtering, showing the anodized alumina hexagonal structure very nicely. For the outer contact layer facing the solution, we use gold since it's electrochemically stable and also a poor water splitting catalyst, which is a good thing for us. The test setup shows the device that is sealed between two electrolyte chambers, and we operate the ratchet using a signal generator, typically a square wave signal with varying amplitudes, frequencies, and duty cycles. The simplest measurements that we can perform here while the ratchet is working is of the open circuit potential or the short circuit current between two silver chloride electrodes, or just reference electrodes. And this is an example test cell that we built in our lab. Each half cell here is about 2 milliliters in volume. And a typical test sequence that we perform to analyze the performance of the ratchet is a duty cycle sweep. In this example, the electrolyte is 0.2 millimolar KCl, and we applied a signal with a frequency of 2.6 kilohertz. The sequence is that we operate the ratchet with a certain duty cycle, then we turn the ratchet off for a short period to return to equilibrium, and then we start again with a different duty cycle. And the duty cycle is the percent of time that the input signal is at the high voltage level. So, for example, the first on period is with a 0 duty cycle. So this actually means that it's a constant voltage with minus 0.3 volts. And the second on period is now an alternating signal that is 14% of the time at plus 0.3 and the rest at minus 0.3, and so on with increasing duty cycles. So first we can notice that when we apply a constant voltage, we get the anticipated fast capacitive charging and discharging response. However, when we start alternating the signal, we see that we get a non-decaying output voltage that is being built up. Okay, so this is this value here. On the bottom graph, we draw the output voltages as a function of duty cycle, and we can see that we get here a sinus-like behavior, which is a hallmark of highly symmetrical ratchet systems. The non-transient output voltage that we see here shows that we have a constant driving force for ion transport. On the next graph, we see the frequency response of two different solutions with similar ionic strength. The signal was a square wave with a duty cycle of 85%. We can see that the KCL curve, we can see that the transport direction is inverted at a certain frequency, and there is a range of frequencies where the ions in the two solutions are transporting in opposite directions. These results are initial and needs to be reproduced in a more controlled setup, but we can say that the observed current reversal is quite interesting, and it's also consistent with other published Ratchet findings. So the question is, can we selectively separate different ions in a mixture? So far we mentioned selectivity only in the context of tuning the frequency to drive a certain particle faster or slower. But ratchets are actually far cooler than that. There is a known but not completely understood phenomena in certain ratchet configurations that the direction of motion of a particle can even be reversed. And we also observed this in some of our tested samples, and we also saw this in the previous slide experimentally. So to see if we can use this for ion separation, we simulated a 1D time-dependent ratchet response to the shown sawtooth potential distribution. And we calculated the mean steady-state ion velocity for a matrix of frequencies and diffusivities, focusing on relevant ranges of diffusivities for most ions. We can see that the inversion frequency changes with diffusivity. So this result has considerable implications since it enables to tune the frequency in order to separate between even same charge ions. For example, monovalent cations like lithium from sodium in seawater, or between potassium and sodium in a biological setting. A task that was so far was extremely challenging. This feature might also be used for instance, for single membrane desalination, since it might allow transporting both sodium and chloride in the same direction. So, we've shown that electronic ratchet mechanisms can be used to transport ions in steady state with no Faraday reactions. We've also shown that RBIPs can separate ions according to their diffusivity and drive same charge ions in opposite directions, which is a unique feature of ratchets that's not possible in any other separation technology. And we're working toward demonstrating real-life ion separation applications. I'd like to thank Dr. Gideon Segev, my advisor, who's also here in the conference, the Boris Mintz Institute, for the support of the research, and this is a list of our collaborators in the University of California. And these are our contact details here, so you're very welcome. Come and talk to us about this exciting project. Thank you.